Now let's take a look at a few examples. So for example number 1, we have somebody sitting at rest at their desk. When drawing our free body diagrams, we're always going to start with gravity. And gravity, just like we said before, points down. Then we're going to think, are there any forces acting in the opposite direction? Well, if we're sitting at our desk, it means that we're sitting on a surface. So therefore, we have a surface. Since we have a surface, we're going to have a normal force pointing perpendicular from that surface. In this case, that's going to be straight up. Are there any forces acting on us in the left or right direction? No, it just says that we're sitting there. It doesn't say that we're being pushed to the left or pushed to the right. It just says that we're sitting at rest. We know that all these forces are balanced because we know that we're at rest. And balanced forces, like we said before, refers to being at rest or a constant velocity. In this case, it's at rest. Example number 2 is us driving in a car at a constant velocity. So again, constant velocity is going to mean that these forces are balanced. Like we said before, we always want to start with gravity. Then from there, we need to think, well, what is our car driving on? Well, it's not a flying car. We're not there yet. So our car is driving on the ground. A ground is the surface. Therefore, we're going to have a normal force pointing up from that surface. Why is the car moving at a constant velocity? We can assume that the engine or something is applying a force that is pushing that car to the right or left. In this problem, we're going to say that it's applying a force to the right. And then we know that because this object is moving, it's also experiencing a force in the opposite direction of its motion. And that force is just going to be friction. We can see that all of our forces here are balanced, meaning that all of the arrows have the same size. Because they're balanced, we said it can mean one of two things, either moving at a constant velocity or at rest. We can see that friction and force applied are balanced here. And we know that the car is moving at a constant velocity, so it's moving at a constant velocity to the right. We know it's moving to the right because friction points in the opposite direction of motion. The other forces that we can see are balanced are gravity and normal. And if we're thinking about our car, we have two options here. Either it's moving at a constant velocity up and down, or it's at rest up and down. Well, I don't know about you, but when I drive my car on the road, it stays on the road. So therefore, since these two forces are balanced, we're going to say that it is at rest in the y direction, meaning that it's not moving up or down. Example number 3, you are accelerating while driving your car. Well, here's our key word here, accelerating. And we already know that accelerating is referencing the fact that we have unbalanced forces. So let's go ahead and label our forces just like we did before. Always start with gravity. We have gravity pointed down. Again, this car is on the ground. We do not have those flying cars. I did just see an article though, and maybe if you're listening to this video 20 years in the future, we will have flying cars. But at the moment, the closest they have got is in Japan, where they produced a prototype flying car. And I believe they said hopefully that they'll have them up and running by 2030. Because our car is not flying, it's on the ground. Because it's on the ground and it's a surface, we have a normal force pointing up. Our car is accelerating, and our car is going to accelerate to the left or right. We're not given enough information to know which way, but for the sake of this problem, I'm just going to say that the rightward direction is where we're moving. Therefore, I'm going to have a big force applied to the right. Since my car is moving to the right, it means I have friction in the opposite direction. So I'm going to have a smaller force friction pointed to the left. It's very obvious that force applied and force friction are unbalanced because force applied is so much bigger than force friction here. Therefore, the applied force is stronger, which is what's making that car accelerate. Force normal and force gravity are both equal and balanced, which just means that my car is not moving up or down in the y direction. Here's our last problem. You are decelerating with your foot off both the brake and the gas pedals. So decelerating is just a fancy word for saying negative acceleration. Well, we see the word acceleration here, so that's going to mean, again, that we're unbalanced. Identifying our forces like we've done before, we know gravity points down. Again, this car is on the ground, it's on a surface, so we have a normal force pointing up because we're assuming that we're driving on a flat ground. If we were driving on a hill, we would have a different free body diagram. But for the sake of the problem, let's keep things simple and say that we're just driving on a flat street. So now we need to look at our problem and see that we're decelerating with our foot off both the brake and the gas pedal. This means that nothing is being applied to the right to move us. So therefore, we are not going to have a force pushing to the right anymore. Well, what's slowing us down? The only thing slowing us down in this case is going to be friction. So we're just going to have force friction pointed to the left. And since there's no other forces on the right side, force friction is unbalanced. We are decelerating because our force friction is unbalanced. And like I said before, there's no applied force. So the only force acting on this object in the X direction is friction, therefore making our car slow down. So if friction is acting in the opposite direction of motion, it's going to be slowing my car down. Just to summarize what we talked about, when drawing free body diagrams, make sure you're identifying what forces are at work in your problem. Always start with force gravity. Then from there, think if you have a surface. If you have a flat surface, then you know that you have force normal. If you don't have a surface, then you don't have force normal. If your object's moving, then you have force friction. And force friction is going to act in the opposite direction of motion. If your object is being pushed or pulled, then you'll have a force acting in that direction as well. If your object is just moving with no forces being applied to it and it's slowing down, then you will only have force friction acting in the X direction. Again, just make sure that you're reading the problem carefully and you're identifying whether that object's on the ground or in the air. Because if the object is in the air and we're ignoring air resistance, then the only forces that can act on an object in the air are gravity. And that's because gravity is a distant force where it doesn't need to be touching the object for it to impact its motion.